going to be doing a short screencast about phase diagrams. And the reason why we're talking about phase changes is we're looking at the effects of intermolecular forces. So IMAs, intermolecular associations, we've already discussed, and one group of you have already done a little lab exercise. The other one will do it tomorrow, where we look at the effects of IMAs on solubility. So things that are polar tend to associate with other things that are polar, polarity. Things that are nonpolar use mostly London dispersion forces. Those dispersion forces mean that you're going to have nonpolar things that will tend to interact with nonpolar things. But another thing that IMAs affect are phase changes. How tightly are the molecules bound to each other? If they're bound very tightly to each other, it's going to take more energy to break the bonds of the solid and make it into a liquid, and take even more energy to break the bonds of the liquid and break it into a gas. So these also affect phase changes. And we're going to be looking at how phase changes are measured, how we represent them, but it should be fairly intuitive that the stronger the interactions, the more likely they are to stay solid or liquid at even higher temperatures. What this adds in is the effect of pressure. And so this is a really simple phase diagram. On this axis, you have pressure, and on this axis, you have temperature. Now, if you just hold pressure constant, say at 1 atmosphere, let's see, this is probably, let's call this around 101.3 kilopascals. As I increase the temperature, I'm going to be solid for a while. Let's go to a thinner line, red. Well, I'll be solid for a while, and then at some point I will melt and become liquid, and then at some point I will boil, the liquid will boil and become gas. So you go from solid to liquid to gas as you raise the temperature. But temperature is not the only thing that affects the transition between solid, liquid, and gas. As we've looked at and alluded to, and actually talked explicitly about earlier, as you change the pressure, you can also affect the state of matter. So we can boil, something like dust off can boil at room temperature if we open it up to atmospheric pressure, but under higher pressure inside the can, it stays a liquid. So in that case, if I'm keeping, say, the temperature constant, say at, 21 degrees Celsius, if I'm starting with a liquid, I might be able to convert it back to a gas by going to lower pressure. So now it's substantially lower pressure. Something that's a liquid, as I reduce the pressure, may boil. So as I'm going down this way, or going up this way, as I increase the pressure, I might convert the liquid to a solid. And that doesn't happen for water for a very specific reason we'll talk about in a minute. So those two things, pressure and temperature, affect whether something's a solid, a liquid, or a gas. If I decrease the pressure on dry ice at room temperature, it will go directly from solid to gas, or sublime. Let's take a look at, actually, this diagram has a little bit more information on it. So this point here, very, very cleverly called the triple point, is where you can have, it's the temperature and pressure, a specific temperature and pressure at which you can have all three phases, solid, liquid, and gas, at the same time. If I am transiting along this line, if I'm going in this direction, as you can see here, I'll just use this. If I'm going in this direction, I'm melting, I'm going from solid to liquid. If I'm going from this direction to that direction, I'm going from liquid to solid. Similarly, at liquid, I can go from liquid to gas, or I can, which is vaporization. So going from solid to liquid is melting, going from liquid to solid is freezing. Those are not new terms to you. Going from liquid to gas is vaporization, not really a new term. Condensation, going from gas to liquid. You see that happen all the time on the windshield of your car or other things like that. From gas to solid directly is called deposition. This, by the way, is how they make synthetic diamonds. And going from solid to gas directly is called sublimation. We talked about that a little bit in the last chapter. Sublimation commonly is what dry ice does. So you take, as I said, solid carbon dioxide, it will sublime directly. Anywhere along the lines here, along that line, are a combination of temperatures and pressures at which I can have both gas and liquid. Anywhere along this line is a combination of temperatures and pressures at which I can have both solid and liquid. Triple point is where you can have all three. And then along the sublimation line is a place where I can have both solid and gas together. So when you're looking along the line, you can see where you are, what the transitions are. I want to talk briefly about something about water and add a little bit more information. So this diagram, once again, has the triple point, looks fairly similar. It goes to higher pressures, and you can see once you get up here, you get what's called a compressible liquid. Everything above this line, as this curve starts to S back the other way. This is a liquid that as I increase the pressure, I'm actually making it into a lower volume. So it's fairly high temperature, fairly high pressures for many compounds. The next 2 points I want to point out is something called the critical point. All right, so that is a temperature and pressure. So you have both an X component, a Y component here, and an X component here. Defines the critical temperature and the critical pressure. Above that point, liquids and solids simply cannot exist. So above the critical temperature, you always have gaseous phase, but if I go to really high pressures, what I end up getting is something called a supercritical fluid. This is not a type of matter that you encounter in your everyday life, but you're going to wonder when you look at the graphs that are presented in lab archives, in WebAssign or some other places. What goes on up here? What's going on this? Is this a continuation of the line? The answer is it's not. You get this little point here, this critical point here, where you now have a little rectangle where you're really not getting a liquid or a gas. It's what's called a supercritical fluid. And so, again, we've got these intersections of these various lines defining important points along the X and Y axis. Critical pressure and critical temperature converge at the critical point. And then the pressure that's consistent with triple point and the temperature consistent with triple point converge on that. The last thing I want to point out on this graph is this line here. This is the anomalous behavior. So if the green line is sort of a normal compound, this is the rather anomalous behavior of water. And that's a really weird thing about water, in that as you increase the pressure, you notice how this line goes backwards, leans back the other way. As I increase the pressure, the melting point actually shifts to a lower temperature. That's because ice has a lower density. The packing of the molecules is actually farther apart than it is in the liquid phase. And so putting it under pressure actually shifts the melting point to a lower temperature. And that's very unusual. And that has to do with some of the weird behaviors of water. The reason is that when you form a crystal lattice of water, which is diagrammed here, you get this very, very strong hydrogen bond interaction. And again, hydrogen bonds are considered the strongest of the weak interactions, of the intermolecular associations on a unit by unit. But they're also extremely directional. They have a very ordered arrangement. Now, when water is in its liquid state, the hydrogen bonds are continually being broken and reformed, and the water molecules are sort of rolling over each other. That's what give any liquid its properties, right? The fact that the molecules can slide past each other. Once you freeze into ice, they adopt a very rigid arrangement. And although, to be perfectly honest, there are at least 11 different forms of ice crystals, the most common form you're used to has actually an increased distance between the molecules, which ends up with ice being less dense than water. And so that's the reason why water shows this rather odd behavior, where as you increase the pressure, you actually favor a lower um, boiling point, a lower melting point, which is the exact opposite of what you see most of the time as I increase the pressure on a normal content and on a normal compound. I require more energy to get those molecules to separate because the pressure is keeping them together. Let's take a look at a typical water phase change diagram. In this case, we're looking at temperature on the y-axis here, and we're looking at input energy in kilojoules on the x-axis. And you've done part of this diagram already, right? We had ice that we were freezing and melting in the beginning of the year, and as we raised the temperature, as we input energy, the temperature went up, and then it plateaued for a while, and that was when the energy was going to break bonds. And then once it was all liquid, we increased the temperature. We didn't go all the way to boiling, but if we continued, we'd get another flat point of the curve at 100 degrees, where we're breaking the bonds of water and converting it into gas. I'm going to label a few points on this graph so you can use them when you look at the WebAssign 10.2. So here, this is how much does the temperature go up per unit input energy. Remember, that's the specific heat capacity. Of ice. And that's joules per gram per degree Celsius. How many joules do I have to put in to get an increase in temperature? The amount of change in temperature over the amount of energy put in. Over this interval here, this is the enthalpy of fusion. Now, the enthalpy of fusion, that's actually the negative. That's the energy that would be released as the bonds of ice are forming. So actually, at this point, if you're going from solid to liquid, that's input energy needed to break the bonds. So it's actually kind of the opposite direction of fusion. Typically, you would have a negative here. But of course, if I'm going from solid to liquid, that's input energy. That's going to be a positive. So it's negative if you're going from liquid to solid because you're forming stronger bonds and that's releasing energy. The rest of this curve is just the specific heat capacity of water. Remember, we abbreviated C, specific heat capacity of water, and that's, we know already, 4.18 joules needed per gram to go up 1 degree Celsius. This interval here is the heat of vaporization, or enthalpy of vaporization. Water is going to stay at 100 degrees Celsius as you're putting in more heat, and you'll need to convert all of that water to vapor, similarly to what happened down here when we were looking at the conversion from ice to water. And then actually, finally, the last little bit, I'm running in a room, that's the specific heat capacity of vapor, of H2O gas. So you're going to get questions about how much energy is needed to go from, say, ice at minus 5 degrees to water vapor at 105. And you're going to need to add up everything you need. You'll need to know how many grams. So if I have, 100 grams of water, initially I'm going to be raising 100 grams by 5 degrees. So that's going to be whatever the specific heat capacity of ice is, times 100 grams times 5 degrees. That's how much energy would be needed to go from here to here. Then I'd need the enthalpy of fusion, which is often given in kilojoules per mole. So you're going to need to convert to grams if we're dealing with water or some other compound. But that's the amount of energy that's going to be needed to take all of the ice and melt it. Then I'll have the specific heat capacity of water going from 0 to 100, that's 4.18 joules per gram per degree, I need 41,000 joules to get up there. And then finally, next step, I'd need the energy needed to convert it all to gas, and I do the math on that. And then finally, the amount of energy needed to raise the temperature of the gas to 105 degrees or whatever the final was. So that question is going to require you to take all of the constants they give you and calculate how much energy there would be needed to raise the temperature of the ice, to melt the ice, to raise the temperature of the water, to gasify or boil the water, and then to raise the temperature of the gas. And that'll take you through that long problem. I think I will stop there.